Hello dear students. So this way we have come to the end of unit first, electrostatics. So today will be the last lecture of that first unit. So these topics that I will be covering today in my lecture, so those are not directly included in CBSE curriculum, but for other state boards and ICSE, these three topics are important. So the first topic that we will be beginning today is lightning conductor. So this is Naren Kumar Devedi welcoming you all in my channel, Naren Kumar Devedi, the physics lover. So let's directly start the topic, lightning conductor. As students, you might have seen a tall conductor standing on generally tall, very costly buildings. So that conductor is there at the topmost position of tall buildings just to protect those costly tall buildings from the lightning effect, generally usually in rainy season. So how does that lightning conductor work? Let's see. Suppose here we have clouds, and clouds carry charges positively, and this lightning conductor is generally consists of pointed end on one side, and the other side is connected with a long thick copper strip. This is long thick copper strip. So this long thick copper strip is properly earthed with the help of, this is long thick copper strip and is being earthed with the help of metal plate in earth. Now this is thick copper strip and ground. And here we have tall building, So this is our lightning conductor. So here, as clouds carry charges near to the building, then the oppositely charges are induced here on this metal strip. So here positive charges will be there and negative charges are here close to this surrounding. As clouds come near to the tall buildings, then the charges are induced on the pointed end of this lightning conductor, and here negative charges are there in the surrounding close to this cloud. So due to the discharging action, the opposite charges are sprayed to the surrounding, which neutralizes the charge on the cloud. If cloud discharges, it discharges through this metal thick conductor or lightning conductor, protecting the building from lightning effect. So this way this lightning conductor is there on top of the building to protect it from lightning effect. Okay, so now let's have next topic, discharging action of sharp points, corona discharge. Remember students, this corona is not there, which is now present around us in the world as in the form of pandemic. It's not that corona. So let's start this topic. Now for this, consider a spherical conductor having radius capital R with charge capital Q on its surface. So the surface charge density sigma is given as charge per unit area. So students, at the pointed end, this radius R is very small, and as can be seen, sigma is inversely proportional to radius. So sigma, surface charge density, is very large, and due to that large surface density at pointed ends, the air coming in contact gets similarly charged, and by the repelling action, those charges in the air are repelled away, repelled back. This produces electrical wind, and by this action the charges are continuously driven away from pointed end of conductors. This process of spray of charge is called corona discharge. Okay, now let's have next topic, Van de Graaff generator. So it's basically an electrostatic machine which was designed in 1931 by R.J. Van de Graaff in Princeton University. Earlier it gave 1.5 mega electron volt, 1.5 mega electron volt energy, and later on it gave 8.5 mega electron volt, and now it is so designed that it is capable of providing 20 mega electron volt energy. So now let's see about the principle. Van de Graaff generator basically works on the discharging action of points and collecting action of spherical conductor. So it works on discharging action of points and collecting action of hollow conductor. So this is the working principle of Van de Graaff generator. Now let's see theory. So for theory, suppose we consider a large spherical conductor, I must say spherical conducting shell, that would be better to say. A having say radius capital R and charge capital Q plus. Now potential inside the shell let we call it V1, and this is equal to 1 upon 4 pi epsilon naught charge on the shell upon radius of the shell. Good. Let me assume a small conducting sphere of radius small r having charge small q kept at the center of this spherical shell. So the potential at the surface of A due to B, let me call this to be V2, which is equals to 1 upon 4 pi epsilon naught charge on the R radius of conducting shell. Now potential due to V at the surface of V, let me call this to be V3, which is equal to 1 upon 4 pi epsilon naught Q charge on sphere upon radius of sphere. Okay, now hereafter we calculate the total potential. So we write now total potential at the surface of A, that's, let me call it to be V1, and this is equal to V1 plus V2. So here we actually had 1 upon 4 pi epsilon naught. This was the common term. Now here it was Q by R plus small q by capital R. Okay, now thereafter we can write total potential at the surface B. Let me call this to be VB, and this has to be equals to V1 plus V3. And now V3 we have this thing 1 upon 4 pi epsilon naught Q by R plus Q by small r. Now we have both potential on conducting shell and the metal sphere placed at the center of shell. So we can now talk of potential difference between sphere at the center and the shell. So the potential difference let me call this to be V equals to VB minus VA, and this will be equals to, as can be seen, this Q by R, and this Q by R will get cancelled. Q will be common in both, so 1 upon R minus 1 upon capital R. Q upon 4 pi epsilon naught 1 upon R minus 1 upon capital R. Now if the sphere B is connected to the conducting shell A through conducting wire, then the charges will start flowing from the sphere, metal sphere B, to the shell A, as the shell A is at lower potential and sphere B is at higher potential. So this way the metal sphere discharges, and those charges, a metal sphere being point charged, so that action on metal sphere B, small point metal sphere B, is discharging action, and those charges which are passing through that conducting wire connecting B and A, those are being collected by the conducting shell A. So this is the working principle. Now let's understand the construction and working of Van de Graaff generator. Van de Graaff generator consists of a large, highly polished metal sphere S, which is also called metal dome, and it is kept insulated from this ground with the help of insulating supports, and a sharp metal spike, which is also called COM1, is connected with the help of high voltage rectifier, which generates the voltage of 5 to 20 kilovolt, 20,000 volt, and at such large voltage here the air gets ionized, and these charges which are produced, they travel through this conveyor belt, which is made of insulating materials, generally rayon, silk, rubber, etc., which runs over pulley P1 and P2. Now these P1 and P2, they are also called roller. So P1 is driven with the help of motor M. Now these charges which are sprayed with the help of this C1, comp C1 metal spike, they reach close to this metal spike C2, which is connected to metal sphere S or metal dome. They are well connected with the help of this C2, and hence these charges reach to the surface of metal dome S. So this way, as more and more charges are created here and they travel through this conveyor belt to reach to metal spike C2, and they are well connected by metal dome S. So this way charges gets accumulated here. Now due to the large accumulation of these positive charges, the potential goes on increasing, and this large accumulation of charges on this metal dome S prevail the condition of leakage of charges. Just to prevent it, the surface of this metal dome is made extremely smooth, and this whole apparatus is enclosed within the chamber filled with gas, and that gas taken generally is methane, freon. The pressure inside this enclosed chamber is kept around 15 atm atmosphere. At a particular stage, when the rise in potential stops, that time the rate of leakage of charge is just equals to rate of transfer of charge to the metal sphere. The gas discharge tube D, which is at the head of long tube D, is the source of positive ions, and the lower end of this tube T is connected with the target, which is properly earthed. Now these positive ions, which are generally deuterons, protons, these positive ions travel through this long tube and reach to the target, and they gain proper energy, and the energy gained by positive ions is Q into V. This generator can also be used to accelerate negative charges, and here the comp C1 will be kept at negative potential, and these negative charges will be traveling through this conveyor belt, and here at the metal dome negative charges will be accumulated. So the process will be just reversed to this one. Now let's see the application part. We can say Van de Graaff generator is generally used to accelerate the positive charges, positive ions like protons, deuterons, alpha particles, etc. for the nuclear disintegration purpose. Okay, students, so let's have chapter and numericals. Okay, so first question, I'm just reading it out. Two isolated metallic solid spheres of radii capital R and 2R are charged such that both of these have the same charge density sigma. Means the sphere of radius small r, capital R, and the other of 2R, they both have same surface charge density sigma. The spheres are located far away from each other and connected through a thin conducting wire. They both are kept far away and are connected through conducting wire. Find the new charge density on the bigger sphere. The bigger sphere of radius 2R, what is the surface charge density that the question is asking from us. So let's start. So for the solution part, we can say the charge on sphere of radius capital R, so that Q1, let me call it Q1, and that is equals to 4 pi R square area into surface charge density sigma. Now, similarly, the charge on sphere of radius 2r, let me call this to be Q2, and that is area 4 pi into 2r square into surface charge density. It is given in the question, same. Okay, now hereafter we can write about capacity of sphere of radius capital R. Let me call this to be C1, and this is 4 pi epsilon naught into R, capacity of spherical conductor. Now capacity of sphere of radius 2r, let me call this to be C2, and this is 4 pi epsilon naught into radius of the bigger one, 2r. This way, now when they are connected through the connecting wire, small thin connecting wire, so the charges are transferred from the capacitor, we can say, or sphere of larger potential to the capacitor or sphere of smaller potential, and this charge continues, this transfer of charge continues so long as they both are at common potential. So let's write common potential. So that common potential we can write V equals to total charge, that is Q1 plus Q2 upon total capacity, that is C1 plus C2. Now let's place these all values in this. So we have 4 pi r square sigma plus 4 pi 2r square sigma upon, here it is 4 pi epsilon naught into r plus 4 pi epsilon naught into 2r. So students, you just solve it, you will be getting approximately 5 sigma r upon 3 epsilon naught. So this will be the answer after solution of this. Now hereafter we can talk new charges at this potential. New charges, what are the charges on smaller and bigger sphere? So new charge on bigger sphere, let me call this to be Q2 dash, which is equal to C2 into V, and this is 4 pi epsilon naught into 2r into 5 sigma r upon 3 epsilon naught, which is equals to 40 pi sigma r square upon 3. Now this is the charge, and area we know 4 pi into 2r square. So dividing that charge with the area, we can have the surface charge density with us. New surface charge density sigma dash equals to Q2 dash upon area, that is 4 pi into 2r square, 5 by 6 sigma. So that will be the answer, 5 by 6 sigma. Okay, now let's have next question. A parallel plate capacitor contains one mica sheet of thickness D1 equals to 1 D1 mica sheet equals to 1 into 10 power to minus 3 meter, and one fiber sheet of thickness D2, which is equals to 0.5 into 10 power to minus 3 meter. The dielectric constants of mica and fiber, let me write this, K1 equals to 8 and K2 that of fiber 2.5. These are dielectric constants given respectively. Fiber breaks down in an electric field breaking down, or you will call this is electric field breakdown strength, that is electric field fiber breaks down at electric field of 6.4 into 10 power to 6 volt per meter. Now what maximum voltage can be applied to the capacitor? So this is the question. Let's start solution part. So here we can write E1 equals to sigma upon K1 into epsilon naught, and E2 equals to sigma upon K2 into epsilon naught. Now here from just cross multiplying, these both will give the value of sigma and we can equate them. So we have K1 epsilon naught into E1 equal to K2 epsilon naught into E2. So here from epsilon naught will get cancelled, and we have the value of E1 max equal to K2 upon K1 into E2 max. Now thereafter we can just calculate it as values are given. K2 is 2.5 upon K1 is 8, and we have maximum value of this 6.4. Actually this breaking electric field fiber breaks down. So it's not mica, it's fiber. I must write it with E2. So this is 6.4 into 10 power to 6. So just solving it, will be getting 2 into 10 power to 6 volt per meter. Now we can talk of maximum voltage that can be applied. So maximum voltage that can be applied is equals to, this is E1 max that we have just calculated into D1 plus E2 max into D2. We can write E1 max into D1 plus E2 max into D2. Now placing these all values, so we have now 2 into 10 power to 6 into 1 into 10 power to minus 3 plus E2 max 6.4 into 10 power to 6 into how much? D2.5 into 10 power to minus 3. So just solving it, will be getting 2000 for this thing, and for this thing we'll be having 3200. Now with this we will be having 5200 volt. So this is the maximum potential that can be applied. Okay, now let's have next question. In the circuit shown in figure, the key K was initially in contact with the terminal A. What amount of heat will be generated in 500 ohm resistance when the key K is brought in contact with terminal B? So the diagram given in question, third, so here a capacitor is there of capacity 500 microfarad, and a resistance is connected here of value 330 ohm, and here we have a resistance of 500 ohm, and this is the terminal B. Now there is a key, and this end is connected with this key like this. Now here we have terminal A, and this is connected with a battery 200 volt, and this is like this. So the question states, when this key K is pressed or connected with terminal A, so this capacitor is charged. Now later on, just removing this key K from here and connecting it with terminal B, so what amount of energy will be dissipated, or what amount of energy will be generated across this 500 ohm resistance? That is the question. So it's quite obvious that when Kp is brought in contact, capacitor stores electrostatic energy, and that stored energy will be equals to half CV square. Now connecting this key to terminal B, that energy will be driving the current through this, and the heat energy will be evolved around these resistors. So the ratio of heats produced in 500 ohm resistor and 330 ohm resistor will be how much? The ratio of the resistors itself. Now we can talk of heat produced around this 500 ohm resistor. So heat produced in 500 ohm resistance, which is equals to this ratio 500 upon the sum 500 plus 330 into energy, total energy, half CV square. Now just placing the values, we have heat produced equals to 500 upon 830 into half into C is 500 into 10 powers to minus 6 in farad into potential is 200 square. So 200 square. Just solving this, we will be getting approximately the 6.024 joule. So this much amount of heat will be. Now let's have next question. A parallel plate capacitor having plate area. Let me write information given in the question. So plate area is given to be 400 centimeters square, means 10 powers to minus 4 meters square. Separation between the plates D equals to 1 mm 10 powers to minus 3 meter is connected to a power supply of 100 volt. A dielectric slab of thickness T equals to 1 mm 10 powers to minus 3 meter and dielectric constant K5 is inserted into the gap. First, find the increase in electrostatic energy delta U. Second, if the power supply is now disconnected and the dielectric slab is taken out, find the further increase in energy. Now third, why does the energy increase in inserting the slab as well as in taking it out? When the dielectric is inserted between the plates, then the energy increases, and even when it is taken out from the capacitor, then also the energy increases. Why? Okay, so let's have the solution part for the first question. So let me just calculate initial when there was no dielectric medium in between the plate of capacitor, in between the plates of capacitor, and later when dielectric is kept, final electrostatic energy, and then subtracting we can have change. So Ui will be equals to half Cv square. So C is half epsilon naught A by D into V square. Now just placing the values, half into 8.85 into 10 powers to minus 12 into area is given to be 400 into 10 powers to minus 4 divided by separation is 10 powers to minus 3 into 100. Voltage is given to be 100 volt and its square. So just solving this, we will be getting 1.77 into 10 powers to minus 6 joule. So this much amount of energy is stored when there is no dielectric medium between the plates of capacitor. Now let's calculate UF, final electrostatic energy. It will be half C dash V square, and now this time half C dash capacity epsilon naught A upon D minus T plus T upon K. This is the capacity into V square. Just place those all values here to have UF. So this is half epsilon naught 8.85 into 10 powers to minus 12 into area is 400 into 10 powers to minus 4 upon this D is 10 powers to minus 3 minus T is also minus 3 plus T 10 powers to minus 3 upon K 5 into V square, that's 100 square. So this way we have those all values there. Now 8.85 into 10 powers to minus 6 joule. This much of energy will be there. Now we can talk of change in energy. So delta U, which is equals to UF minus UI, and we have 8.85 minus that 1.77 into 10 powers to minus 6. So we have here with us 7.08 into 10 powers to minus 6 joule. So this is the final answer for the first part of question. Okay, now second part of question, if the power supply is now disconnected and the dielectric slab is taken out, find the further increase in energy. So the power supply is also disconnected and dielectric is being taken out. So let's calculate the second part. For the second part, we can say Q dash equal to C dash V, and this is equals to 17.7 into 10 powers to minus 10 as the value of C into value of this V to be 100, which is equals to, this will give us around 17.7 into 10 powers to minus 8. Thereafter Coulomb. Thereafter we can write V dash, which is equals to Q dash upon C. Now see, this much charges were stored between the capacitors when the potential was applied. Now it is being disconnected. So the charges stored between the capacitor will remain same, but now the capacity is taken when there was no dielectric. So here we are having C instead of C dash. So now just having the values 17.7 into 10 powers to minus 8 divided by the value of C to be 35.4 into 10 past 2 minus 11. So this way we will be getting 5 into 10 past 2 volts as the value of potential now. Now let's have change in electrostatic energy. It is half CV dash square minus half C dash V square. So this is the energy when the supply has been removed and the dielectric has also been removed, and this is the energy when the dielectric was there and it was connected with the supply. Now just placing these values, we have with us half 35.4 into 10 past 2 minus 11 into 5 into 10 past 2 square minus the 17.7 into 10 past 2 minus 10 into 100 potential square. So this way, just simplifying this, we will be getting 3.54 into 10 past 2 minus 5 joule. Now, about the third part of the question, third part is saying what is the reason of increase in energy when the dielectric slab is inserted and when it is taken out from the capacitor. So for the first case we can see when slab is inserted, so the insertion of slab increases the capacity by a factor dielectric times. So just due to the increase in capacity, the electrostatic energy increases. So capacitance increases by K. So with this we can justify the increase in energy. Now for the second case, when the slab is removed, that time the electric potential increases. Due to the insertion of dielectric slab, the electric potential decreases, and when it is taken out, the electric potential rises. So due to the rise in potential, the electrostatic energy rises. So here V increases. So this way we can justify. Now let's have fifth question. Consider the situation shown in figure. The width of each plate is small b. The capacitor plates are rigidly clamped in the laboratory and connected to a battery of EMF E. All surfaces are frictionless. Calculate the value of capital M mass for which the dielectric slab will stay in equilibrium. So the diagram given here for the fifth question is, these are the plates which are clamped to the laboratory. This one. Now the plate separation given is D, and this is the length of plate L given, and here dielectric slab is there, K, dielectric constant, and this dielectric slab is further connected with this is suppose the table, the corner of which is connected with a pulley. Suppose this is the pulley and we have here a mass connected. Now these plates are connected with supply like this, and this is EMF, battery EMF E. This is the question given. Now, here actually we will be using the concept that the force applied by this battery when this capacitor is charged, so it pulls this here and the weight pulls it here. So when they are balanced, so this is at equilibrium condition. So let's begin. Now suppose the distance of this dielectric slab is say x, so the remaining distance is L minus x. L minus x. So here, to begin, the capacity C1, here actually we are saying this to be C1 and this to be C2, and they both are connected in parallel. So first let's calculate C1. So this will be K times epsilon naught A. Now what is A? This is plate area, the width of plate given in question into distance moved x. So this is area epsilon naught A by D, separation. This will be the capacitance. Now for the C2 we can write this one. It will be equals to epsilon naught into area B into what is the distance now? L minus x upon separation D. Now, as they both are connected in parallel, so we can calculate equivalent capacitance. So, C equals to C1 plus C2, and this will give us epsilon naught B upon D, a common term. Inside we have L plus X into K minus 1. So, this would be the term obtained after addition. Thereafter, we have this electrostatic force getting balanced by Fe towards this, towards the inner portion of capacitor, and weight will try to drag this electrostatic, this dielectric slab out of capacitor. So here we calculate now work done by battery to produce this situation. That will be equals to change in energy, electrostatic energy, plus work done by force F, this one. Now let me call this work done by battery to be dWB, and this is du, plus this work done by force let me call dWF. Now dWB will be equals to dC, change in capacitance, small change in capacitance, into V square, and this will be equals to half DC into V square, plus this will be F into dx. Now just transposing this term here, we have half DC into V square, which is equals to F dx. Now we can talk of F. So this is half dC upon dx into V square equal to F, and C is this thing. So just differentiating this C with respect to x, half V square d by dx of epsilon naught B upon D into L plus x into K minus 1. So this thing will be there. L is constant. So the differentiation of this will be 0. So this differentiation will give us only this K minus 1. So we have final answer for F to be equals to epsilon naught B upon 2D into V square as constant term. Now the differentiation of this will be K minus 1. Now at this condition, equating this force with M into G, now at static or equilibrium position, this epsilon naught B V square upon 2D into K minus 1 will be equals to mass into gravity. So just transposing G here, epsilon naught B V square upon 2GD into K minus 1. This will be equals to the value of mass that question is asking. So students, this was the last lecture of Unit 1st Electrostatics, class 12. So I hope you have enjoyed learning Unit 1st. So we end up today's session here. Do like and subscribe the channel.